We've previously looked at solids, which are rigid and keep their shape. We'll now discuss fluids, which form to the shape of the container. This also applies to gases. They exert a force on the surface of the container perpendicular to the surface. We define two measurements in fluid mechanics. One is density, given by rho, which is equal to mass over volume, and the other is pressure, given by P, which is equal to force per unit area. The units for density is kilogram per meter cubed, and the unit for force is Newton per meter squared, which is also called a Pascal. Note that the pressure is equal throughout the fluid and does not depend upon its shape, period. Let's look at fluids at rest. So you probably know from diving into a pool that the pressure increases as you go deeper in water, and it decreases as you rise in air. This is called hydrostatic pressure. So let's look at a sample of a fluid. Here we have a container with a fluid, and we're just going to take a sample of this fluid. And there are forces acting on this fluid. You have the weight of the fluid, which is the force of gravity. It was equal to m times g. But there is also a force pushing up on the surface, the bottom surface of the fluid, we'll call that F2, and a force pushing down on the top of that surface of the fluid, which is F1. So if we draw a free body diagram, we will see that we'd have this. Okay. And those are the forces exerted on each molecule in our sample of the fluid. So F1 is the force pushing down on the water sample, F2 is the force pushing up, and mg is the weight of water. Now, this sample of water is in static equilibrium, so that means that force 2 has to equal force 1 plus the weight. So we get no motion. So if we put in the definition of force, that would be pressure times the area equals pressure 1 times the area plus the mass of the water sample times g. Now, if we say that mass is equal to density times volume, okay, which becomes density times, and volume is equal to the area times the change in depth. So if up here we define that as y and x, okay, and this is y1 and this is y2, and we have, if this is our sample of water, okay, in 3 dimensions, we have y1, y2, and here's our area. So density times the area times the height of that sample is. So let's substitute this into this equation. We get P2 times area is equal to P1 times area plus mass, which we know is rho times area times y1 minus y2 times g. These cancel out. And if we solve for P2, we get P2 is equal to P1 times rho plus rho times G times Y1 minus Y2. Now we're going to say that Y1 is at the surface. And that reference would be at Y equals 0. So then we get P2 equals P1 we'll call P0 at the surface, which is atmospheric pressure, plus density times G times a minus Y2. But Y2 is the depth below surface, which we'll call minus H. So again, P2 is equal to pressure at the surface, atmospheric pressure, plus Pg times H. So this equation gives us our pressure at a depth H of a fluid in static equilibrium. What you can see from this equation is that the pressure depends only on your depth in the water, H, and that the shape of the container also does not matter. Now notice that your pressure, P2 at a depth, has two components. That's made up of P0, which is the pressure at the surface, or atmospheric pressure, and rho GH, which is the pressure due to the weight of the water above you, and that is called the gauge pressure. In other words, when a diver goes into the water and he looks at his pressure gauge, this is what he's measuring. But the total pressure on him is P0 plus rho GH, which is P2. And P2 is also called the absolute pressure. Now we talked about pressure going down in water or another fluid, but there's also a change in pressure if you climb up a mountain, a change in air pressure. In this case, the pressure in air is equal to your pressure at the lower surface, which we assume would be at the level of the ocean, minus the density of the air times G times D, where D is the height up the mountain. So this is the equation for your total or absolute pressure as you go up in elevation in the air. So now let's talk about Pascal's principle. Pascal's principle states that a change in pressure applied to an enclosed fluid is transmitted to every part of the fluid and to the walls of the container. So this principle is used to operate hydraulic machinery via the hydraulic lever. And the hydraulic lever is depicted here on the left. And with a hydraulic lever, a force applied over a distance can be transformed into a greater force over a smaller distance, and vice versa. So here you can see we have force 1 pushing down on this tube, and there's a fluid level and volume of fluid here. that force is transmitted equally throughout the tube and comes up on the other side where there's a larger area, and that's pushing up with a force F2. So we know that since pressure is equal to force over area, we have, and the pressures are equal throughout, we know that force 1 over area 1, which is pressure 1, is equal to force 2 over area 2, which is pressure 2. And we can solve such that force 2 is equal to force 1 over area 2 divided by area 1. So let's take an example where area 2 is equal to 10 times area 1. We can then put that into this equation. Force 2 is equal to force 1 times area 2, which is 10 times area 1 over area 1, or force 2 is equal to 10 times force 1. So you can see that you apply force 1 to the smaller tube, and you can get 10 times the force coming up in the larger tube. Now, what about the distance that the piston would travel? Well, we know that volume is equal to area times distance, and the distance here is how far this fluid is pushed down. Okay, so that's equal to area 1 times distance 1 is equal to area 2 times distance 2, because the volume of fluid being moved down and up in these tubes is the same. So if we solve for d2, that's equal to d1 times a1 over a2. And we know that that's equal to d1 times a1 over 10a1, because we said that a2 is 10 times a1. So we get d2 is equal to 1/10 times d1. So this shows that we multiply our force 10 times, but we only move the distance by 1/10 the amount. This is how an hydraulic lever or hydraulic machinery works, based on Pascal's principle. Now, let's talk about Archimedes' principle. This principle states that when a body is in a fluid, a buoyant force, F sub B, acts on the body. It is directed upward and has a magnitude equal to the weight of the fluid that has been displaced by the body. So the buoyant force is given by FB, and its magnitude is given by the mass of the fluid displaced times G. So let's diagram this. Again, we have a body in the fluid, and there's a buoyancy force pushing up on the body, and the mass has a weight, mg. So if we draw the free body diagram, we have the force of buoyancy and the weight of the fluid. And in this case, FB is equal to mass of the fluid times G. Now, if a body is floating on the surface, it's in equilibrium, and the buoyancy force has to equal to the force of gravity, which is equal to the mass of the fluid times G. And what this says is that with a floating body, the magnitude of the force of gravity Fg is equal to the weight of the fluid that has been displaced by the body. In other words, a floating body displaces its own weight of fluid. Another point to note, that if you have a body that is sinking in a fluid, in other words, not in equilibrium, then it still has a buoyancy force pushing up on it. So if you were to weigh that body on land, you'd have the actual weight. However, that weight is reduced in water, and you have the apparent weight is equal to its actual weight minus the buoyancy force. So the apparent weight is equal to its actual weight minus F sub B. Now let's talk about fluids in motion. Now, when we discuss fluids in motion, we will use ideal fluids. Real fluid motion is very complicated and will not be discussed here. So there are four assumptions for an ideal fluid. The first assumption is that it has steady or laminar flow. That means the velocity of the flow is constant. The second assumption is that it's incompressible, which means that its density is constant. The third assumption for an ideal fluid is that it is non-viscous. That means that the fluid has no drag or internal friction. And the fourth assumption is that the flow is irrotational, that an object does not rotate within the fluid. So this brings us to the equation of continuity for a fluid in motion. And this states that the velocity of flow is related to the cross-sectional area it flows through. In other words, let's say we have a tube that goes from a cross-sectional area of A1 to A2, and it has a velocity V1 here and V2 here. Okay, and the fluid's moving this way. This states that area 1 times the velocity 1 is equal to area 2 times the velocity 2, and that is equal to a constant. And that is the equation of continuity. And that could be written another way, that the volume flow rate R sub V, which V being volume in this case, is equal to area times the velocity of flow, and that is equal to a constant. So these are two ways of describing the equation of continuity for a fluid in motion through different size tubes. And in this case, the volume flow rate is equal to the change in volume over time, which could be considered d volume dt. And the unit for the volume flow rate is meters cubed per second. And if the density of the fluid is uniform, then we can also look at R sub m, which is the mass flow rate. And that's equal to density times R sub v for volume, which is equal to density times area times velocity of flow. And that is also constant. Okay, and that's your mass flow rate, and the units for that are kilograms per second. Now, this applies to non-compressible fluids. So now we're going to talk about Bernoulli's equation. Bernoulli's equation relates the pressure in a tube to the speed of flow of the fluid and the height of the fluid. So first, we'll state that a fluid's kinetic energy density is equal to 1/2 density times the speed squared. And this gives you the kinetic energy per unit volume. So Bernoulli's equation then states that a pressure plus 1/2 rho times v squared plus rho gy is equal to a constant. So this is applying conservation of energy to determine the pressure due to the velocity of a fluid and its height. So if we consider the inlet point 1 and the outlet point 2, we could say that pressure 1 plus 1/2 rho v1 squared plus rho g times y1 is equal to pressure 2 plus 1/2 rho v2 squared plus rho g y2. So what Bernoulli's equation also shows is that if the speed of a fluid increases as it travels horizontally, then the pressure of the fluid decreases, and vice versa. Because since this is a constant in this equation, if V increases, okay, then if it's horizontal, then Y is the same, density is the same. Then if V increases, then P has to decrease, and vice versa. So again, as the velocity of a fluid in a horizontal tube increases, the pressure decreases. And this is the principle by which airplanes have a lift. Let's do some problems. A tank of fluid with a depth h has a drain hole at the bottom. What is the velocity of the fluid as it comes out of the drain hole? This is actually a derivation of Torricelli's theorem, which gives the speed of efflux from the tank. So why don't we draw this? We have a tank that comes down, and it has a drain hole at the bottom, and we'll call this area 1, the area of the tank, and that's at a pressure 1. And if this is our y-axis and x, this is at y equals 0, and we'll call this y equals h. And we have an area of the drain hole, A2, and that is at a pressure, P2. So the fluid's coming out, and we want to know what the velocity of that fluid is. So we can consider the tank and drain hole as one tube that goes from area A1 to area A2. We can then use the Bernoulli equation for the system. So basically, it's like having a tube that looks like this. And in this case, our Bernoulli equation says that P1 plus 1/2 rho times V1, velocity 1, plus rho GH 1 is equal to P2 plus 1/2 rho velocity 2 squared plus rho GH2. Okay, so for P1 and P2, they're both open to air, so they're both at atmospheric pressure. So these are equal, so these can be canceled. We can cancel out the density in all these terms. And we know that H2, which is our reference point, we're calling that y equals 0, is 0, so that whole thing could be canceled out. So what we end up with is 1/2 velocity 1 squared plus GH, in this case H1 is equal to H, is equal to 1/2 velocity 2 squared. So if we solve for velocity 2, we get velocity 2 squared ends up being V1 squared plus 2GH. Well, when we look at the system, we can see that the area 1 is much, much greater than area 2. And from the continuity equation, we know that V1 is equal to area 2 over area 1 times V2. So since A1 is much, much greater than A2, we're going to assume then that V1 is so small that it's negligible, and V1 squared is equal to 0. So that means that V2 squared is equal to 2GH. If we substitute it into this equation, or V2 is equal to the square root of 2GH. So this is known as Torricelli's theorem, and it gives you the speed of efflux of the fluid from a tank with a hole in it. Let's do another problem. Water flows through two sections of a pipe. In the first section, the velocity of flow is 3 meters per second, and the pressure is 20 kilopascals. The second section of pipe is 1 meter above the first, and the velocity of flow is 4 meters per second. What is the pressure in the second section? Assume the density of water equals 1. So let's draw what we have. We have the first section of pipe, and that goes into the second section. And we know velocity in the first section is 3 meters per second, and the pressure in the first section is 20 kilopascals. And we know the velocity in the second section is 4 meters per second, and we want to know what the pressure is. And if we look at our axes, we know that this is, we'll call this H1 is 0, and here H2 is equal to 1 meter. Okay, so we can use Bernoulli's equation. So let's write that out. So that's P1 plus 1/2 density times V1 squared plus rho G H1 equals P2 plus 1/2 density times V2 squared plus rho G H2. So let's put our numbers in. P1 we know is 20 kilopascals plus 1/2 rho times 3 squared plus, well, H1 we said is 0 is equal to P2 plus 1/2 rho times 4 squared plus rho G, and H2 we know is 1. So we get 20 kilopascals plus 4.5 rho is equal to P2 plus 8 rho plus rho G. So we're given that the density of water is equal to 1. So we have 20 kilopascals plus 4.5 is equal to P2 plus 8 plus G, which is 9.8. Or we get P2 is equal to 20 minus 13.3, or P2 is equal to 6.7 kilopascals, which is the pressure in the second section of pipe. Here's another problem. Water leaves a faucet with a cross-sectional area of 1.2 centimeters squared and falls downward at 3 meters per second. What is the cross-sectional area of the stream of water at 0.6 meters below the faucet? So once again, we're going to draw this. We have a faucet, and water is coming down, and we know that the velocity 0, we'll call it V0, is equal to 3 meters per second, and the area of the faucet is equal to 1.2 centimeters squared, and it's falling down, and we want to know at 0.6 meters, we want to know what is the cross-sectional area of the water here, and we'll call that A1. So we know that it's falling with acceleration due to gravity g. So from our kinematic equations of motion, we know that if we call it V1, the water stream V1 is equal to the square root of V0 squared plus 2GH. So V1 then becomes the square root of V0 squared, which is 3 squared, plus 2 times 9.8 times H, which in this case is 0.6, or V1 becomes 4.6 meters per second. So now we know V1 and we want to find the area 1. So we're going to use our equation of continuity. And as you know, A0 times V0 equals A1 times V1, or A1 is equal to A0 V0 over V1. And we put those numbers in. So A1 we're given as 1.2, V0 we're given as 3, and we found V1 4.6. So A1 equals 0.78 centimeters squared. So as the water falls down and picks up speed, the area reduces to 0.78 centimeters squared. Continuing with our problems. An iceberg is floating in the ocean. What percent of it is exposed above the ocean surface? Assume the density of the iceberg is 0.92 grams per centimeter cubed, and the density of seawater is 1.03 grams per centimeter cubed. So let us draw this. We have our iceberg, and let's say it kind of looks like this, and we have water and our center of mass, okay, and the volume of seawater displaced is actually equal to the volume of the submerged iceberg. And let's also draw a free body diagram. So if this is our center of mass, we have the weight of the iceberg, and we have our buoyant force. And it's an equilibrium, so these balance. So we'll call that weight of the iceberg. So the buoyancy force is equal to the mass of the water displaced times g, which in this case is density of the water times the volume of the water times g. And the weight of the iceberg is equal to the mass of the iceberg times g, which is equal to the density of the iceberg times the volume of the iceberg times g. So again, because the iceberg is in equilibrium, FB equals WI, or density of W times volume of W times G is equal to density of the iceberg times volume of the iceberg times G. And of course the G's cancel out. And we get density times volume equals density times volume. And we want to solve for the volume of the water displaced over the volume of the iceberg, which is equal to rho of the iceberg times rho of the water. And the reason we're doing this is the volume of the water displaced, as we set up here, is equal to the volume of the submerged iceberg. So we're actually finding out what percent of the iceberg is submerged. So that's equal to 0.92 over 1.03, which is equal to 0.89, which is equal to 89%. So the volume of the water displaced, which is the volume of the iceberg submerged, to the total volume of the iceberg is 89%, which means that the volume of the iceberg that is exposed is 11%. So this is the percent of iceberg exposed above the surface of the ocean. Here's another problem. Water is poured into one side of a U-shaped tube. Then benzene is poured into the other side. This causes the water level to rise to 8 centimeters above the benzene level. What is the height of the benzene column? The specific gravity of benzene is equal to 0.879. So let's first draw this with the water. So we have a U-shaped tube, and this has water in it. Okay. And now we pour benzene in. And let's call this the benzene. And this will be our water. And we're given the height difference between these levels is 8 centimeters. So we can again use Bernoulli's equation, which says that the pressure of benzene plus 1/2 the density of benzene times the velocity of benzene squared plus the density of benzene times G times the height of benzene is equal to pressure of water plus 1/2 density of water times the velocity of water squared plus the density of water times G times the height of water. Now, let's look at this equation. First of all, these tubes and fluids are open to air, so we know that the pressure of benzene is equal to the pressure of water, which is equal to atmospheric pressure. So these equal and cancel out. We also know that this fluid is not moving, so there is no velocity. Velocity is 0, so this cancels out. So what we end up with is the density of benzene times G times the height of benzene is equal to density of water times G times the height of water. The D's cancel out. Density of benzene times the height of benzene equals density of water times the height of water. And we're looking for the height of benzene, so let's solve for that. Height of benzene is equal to the height of water divided by density of benzene over density of water. Now, you may be wondering why I put the denominator in this form. And that is because the density of benzene over the density of water is actually the specific gravity of benzene. Specific gravity is the ratio of the density of liquid to water. So this becomes the height of water over the specific gravity of benzene, which we know that's equal to 8 centimeters over 0.879. And so the height of the benzene column becomes 9.1 centimeters. Here's another problem. A tank of water sits on a spring scale which reads a weight of W. A stone of weight W sub s is then hung from a string and lowered into the tank without touching it. What will happen to the weight the scale reads? So first we have a tank of water sitting on a scale, okay, and we put a stone in here of weight WS, W sub s. So let's draw a free body diagram. But first, realize we have two systems. We have the stone system and the scale system. So if we look at the stone system and draw a free body diagram of the stone, okay, we have tension, we have buoyancy force, and we have weight, W sub s. And for this, the forces balance, and we get tension plus the buoyancy force is equal to the weight of the stone. Okay, and now we have the scale system. Now, in the scale system, if we look at the forces, you have the weight of the water in scale, you have the weight of the stone, you have the tension of the string, and you have the normal force. And the normal force is what you see on the scale as the reading. That's what we're actually measuring. The only thing not affecting the scale system is the buoyancy force. That only acts on the rock. So for this scale system, we know the tension plus the normal force has to equal the weight of the stone plus the weight of the tank in water. Okay, so we'll call this equation 1 and this equation 2. So we want to subtract 1 from 2. So if we take then equation 1 and we subtract T plus FB minus is equal to, and we subtract Ws, we end up with Fn minus F buoyancy is equal to W, because these cancel out. Or our normal force is equal to the weight plus the buoyancy force. So before the rock was put in, we were measuring the normal force. That's the scale reading. And that was equal to the weight of the water in the tank. Once we put the suspended rock in, we actually increase the reading on the scale by the buoyancy force. It goes up by the buoyancy force amount. So that's what happens when you suspend the rock in a tank of water on a scale.